So we're going to get into tank problems. This is still out of section 1.5. It'll take some time to set up and understand what it'll take a moment to figure out how. I'm just going to roll with those interruptions. It'll take a moment to figure out what the problem, the setup is. I'll have to set it up for you guys. But these problems typically use integrating factor, which is what we learned in 1.5 to solve. So let's start with a tank of water. I'm going to have like a pipe that flows out and then a pipe that flows in. It could be any fluid. It doesn't have to be water. I'm going to say that it starts with 100 gallons with concentration 100 liters. 3 grams per liter, right? So
3 grams per liter.
Thank you. Yes, 3 grams per liter. Okay, so it starts with 100 liters in it and 3 grams per liter. So think through that. If I got 100 liters and each liter has 3 grams, how many total grams of some kind of substance or salt or something like that is in there? Just think through that and we'll get there in a moment. But Q, hopefully got 300, okay? But Q is, so this has something in it. This fluid, this water has something in it. And I know that there's 3 grams in every liter. So Q is going to be the amount of salt or other substance in the fluid. In this case, measured in grams. And that's eventually, I want to know what Q is. So when I throw some other things in here, Q is going to be changing over time, and I want to function for Q with respect to time. I'm doing my best here. I got some distractions. But let me keep setting up this problem, and we'll talk about what Q is in a moment. All right, so what I have is I have some water. We'll just call it water. I have some water flowing out of this tank, and I know the rate at which it's going. It's going 2 liters every minute. Okay? I also have fluid, water, flowing in at 2 liters every minute. Now, the water that's flowing in has some of this salt or substance in it. So I actually know the concentration in this problem. So we know that the concentration coming in is, for every liter, there's 10 grams. So the way I would write that is 10 grams per liter. So that is with the inflow. This is the outflow. And then this is what we have inside of that tank. Let me just get rid of those green lines. Hold on. Okay. So let me just repeat the setup and I'll try to do it quickly. I've got a tank. It has some water in it. That water has some salt in it. I have 100 liters of water. There are 3 grams in every liter. I got a flow coming in that has a different amount of salt in it, 10 grams per liter. It's coming in at 2 liters per minute. And then I know that it's leaving at 2 liters per minute. One thing that's key with this problem that makes it a little bit easier than some of the other ones is that the inflow rate and the outflow rate are the same. That means that we start with 100 liters, and while the amount of salt in this tank changes, the volume of the tank does not change. And that simplifies our problem here. So what I want to do, I want to solve for Q. I want an equation, Q of T equals. That's the goal for this problem. So we need to go back to something that I was talking about a moment ago, and that is Q of 0, right? That is the amount of salt at time equals 0. Now let's go back to this. I have 100 liters, and I have 3 grams in every liter. You should know from like chemistry and stuff like that. Well, one, you might just see, all right, there's 300, but I can do some dimensional analysis and multiply those two. The liters cancel, and that gives me 300 grams. And now that should make sense. I have 100 liters. Each liter has 3 grams. How many grams? 300. We're going to use that in a little bit. So that is Q of 0. Okay, so let's set up this problem. I probably should just zoom out for a moment. Okay, so, well, I'll zoom out when I need that info up top. So, dq dt. This is what I'm going to focus on. That is the rate of change, WRT in calculus typically means with respect to, right? So it's the rate of change with respect to time of the amount it's the rate of change with respect to time of the amount of salt in the tank. Okay? So the units of measurement of dq dt, well, look, Q, what are the units of measurement of Q? Well, it's grams, right? We know that up here, right? Q is measured in grams. And what's the measurement of time? Well, in this case, it's minutes, right? So the units of measurement of Q of T, or sorry, of dq dt is going to be grams per minute. And this becomes super important for solving this problem. Okay, so let's do it. Let's set it up and solve it. So dq dt. Remember, it's grams per minute. I am going to look at in grams per minute, and then I'm going to take out, grams per minute. So I'm looking at the in rate for this problem minus the out rate for this problem. Now I will pause for a moment. All right, I brought the problem down here so that we don't have to scroll up and down, right? So oh, missed the top of the pipe. Okay, so in. Notice I want to get grams per minute. That is my key. So I also lost that, grams per liter. Okay, so what I do, notice it's really easy to get, this is the inflow. This is the information about the inflow, 2 liters per minute at 10 grams per liter. So watch, if I multiply 2 liters per minute by 10 grams per liter, liters cancel. What are the units of that? It's grams per minute. That matches what I have over here. So, and that's the in, that's the information for what's coming in. So I have figured out what grams per minute is for anything that's coming, for the thing that's flowing into this tank. I missed that too. Okay, so now let's do it for the out. For the out, look, I know it's going out at 2 liters per minute, right? Same as it was here. I got 2 liters per minute. So minus 2 liters per minute. Now, I know I've got 100 liters, right? So what I'm going to do is multiply by, and I'll go like this, put a little fraction. Just like I canceled the liters down here, because there were 10 grams per every liter, I know that it starts with 100 liters. And I'll give you another way to think about this too, because this here was the concentration, right? So the question is, where do I get grams for what's coming out of this tank? Well, notice, if I go back up, Q of T. Q of T is the grams of salt in this tank, right? So if I come down here, I'm going to put my Q right there, because Q is in grams and it's what's flowing out. Now, the other way to think about it, the in is the inflow rate times the in concentration, right? So the out is going to be the outflow rate times this little fraction right here is just the out concentration. How do I know that? Because Q, it's always, what is concentration? It's grams per liter. So what's the concentration of this fluid in here? We're assuming that it mixes evenly. What's the concentration here? It is Q, which is the amount of grams, divided by the number of liters that's in there, over 100. So, let's keep going. Let's just simplify everything here. So that's the full setup there, right? So let's go and simplify what we have here. I'm going to write dq dt as q prime just to make it simple. So I'm just going to rewrite that line there. Equals. All right, look, all I have here is 2 times 10. So that's 20, right? Minus, all right, here I've got 2 over 100, right? So that's really just 1 over 50, and then times Q. So this long process up here with this setup of the problem, what's Q, what's dq dt, in rate minus out rate, figuring it out from the picture, really just gets me down to this equation right here. And this is the equation that I want to solve. So what I want you to notice is that if I move this term over to the other side, I get Q prime plus 1 over 50 Q is equal to 20. Now, this should look super familiar. Why should this look super familiar? It is first order and it is linear. So how are we going to solve this thing? We're going to use integrating factor. What's that? That's the thing with the mu. So I'm going to stop this video here, and in the next video, I will walk through the full solution process of figuring out how to solve this equation, which is not, in terms of the integrating factor questions that you've done, it's really not that bad.